should do something about it.
So it's a real pleasure to open this 15th edition of the workshop on geometric correspondences of gauge theories. Welcome to all of you. I hope you will have nice days of discussions, science, and swimming. And so it is a pleasure to introduce Mukund Rangamani, who's the first speaker, and he will talk about strings and near-extremal black holes in AdS3. Please, you have 1 hour.
Thank you. Thank you. Thanks to the organizers for inviting me. It's a pleasure to be back in Trieste. I was initially thinking of what to speak, and I thought maybe I could talk about some work I did last year with a student from Davis, Frederick Gia, on trying to use conformal blocks to understand quasi-normal spectra. But then I felt like it'd be silly of me to bring to Trieste the Trieste formula. So I decided to change my topic and talk about something different. So the goal is to talk about near-extremal black holes and to explain a particular example where we can do two things. One, we can compute the quantum effects, but not only compute the quantum effects in semi-classical gravity, but also directly in string theory. So that's going to be the main goal, to try to explain to you how black holes, which are stringy, also see features that we've seen and come to appreciate from the semi-classical gravitational path integral that Chiara and Roberto will talk about later today. And in particular, I want to explain one example in this context where there's a large amount of supersymmetry. In fact, the largest there can be in two dimensions, the so-called large n equals 4,4 supersymmetry, where things are rather different than you would believe. This is one example I know where supersymmetry enhancement confuses rather than elucidates. Okay, so I have some horizon, so I will keep to that half. Is that good? People can see here. Great. In the corner, you're also good. Okay, so the goal is to compute the string one loop partition function around BTZ cross X, where X is some 7 manifold, and we could take this to be one of many choices. We could take X7 to be S3 times T4 or S3 times K3, or more ambitiously, the case I'm really going to discuss, S3 times S3 times S1. These two preserve what's called the small n equals 4,4 supersymmetry in 2 dimensions. So they give you and this you can think of as a supersymmetry of the dual CFT living on the boundary of AdS3. This guy gives you the so-called large n equals 4,4 SUSY. I'll explain what the difference is, and I'll explain what the algebras are and why they're different in due course. Yeah. We could do 0,4. So for example, we could do 0,4 very easily by taking these examples, and I didn't say which string theory, so I will do 2B. If you take these examples and do, say for example, this guy, and you do type 2A on S3 cross K3, that automatically gives you 0,4 because it's dual to heterotic on T4, or you could just do heterotic on T4. There is nothing that I'm saying that's going to be relevant to 4,4. I'm just going to do 4,4 because I want to do type 2B. So it's a bit simpler for me. In fact, as you will see, I'll only care about one half of the CFT for some of these stuff. So it's going to be I'll mostly talk about the holomorphic side and let the anti-holomorphic side do whatever it wants. Yeah, so indeed, I know why you're asking, and the answers will be different in both cases. I'll just use this as an exemplar, and you'll see all the features that you want to see in this case. And if you do 0,4, then you either get supersymmetric black holes or non-supersymmetric black holes, depending on which side of the supersymmetry you stick to. All right. So in all these examples, there'll be one. We'll actually not do directly the computation around BTZ. We'll basically do the calculation, the string partition function around AdS3, Euclidean AdS3 with thermal boundary conditions times X7, and this guy will be identified, as I said, with T plus beta. I'll specify some more identifications written on chemical potentials in a second. And the BTZ answer will be a modular transformation of this answer. Okay. So that's one reason to pick this example, because we can actually do first principles computations. So let me say a few words about what the structure is from the string theory point of view for the first bit of the talk, so I can tell you what the ingredients are, and then I'll switch gears and then talk about the algebras that you get and what kind of expectations you would have. So if you think about AdS3 cross S7, X7 as a solution to background of 2B, we'll parameterize this, and we'll have these backgrounds supported by NSNS two-form flux. Okay. So if you want, from first principles, we'll think of these solutions as being built out of taking near horizons of fundamental strings and NS fibrils. The only NS flux in this game, no Ramond-Ramond fluxes. And the string sigma model will be a Vezumino-Witten model because of these fluxes, which is solvable, and it has the following ingredients. It has an SL2 level K from the AdS3 part, and I put a hat here because this is world sheet n equals 1 supersymmetry. I'm doing the usual RNS formalism, and this I can break up into SL2 level K plus 2 bosonic plus 3 free fermions. Okay, so the standard story for n equals 1 WGW models, where the bosons and fermions, the currents interact with the fermions. The fermions are charged under the same gauge group. But by a field redefinition, you can decouple the fermions. They transform as free fermions, and then the remaining, its effect is to shift the currents of the bosonic algebra by some amount. In this case, it's plus 2 because that's the dual Coxeter number of SL2. If you have the three spheres, the three spheres are also given by SU2 level K. Let's call them K prime for SU2, for S3, again with n equals 1 SUSY. And now you can break this up into SU2 level K minus 2 plus 3 free fermions. And this is bosonic. And finally, if you have the circle or the T4, they're just given by free bosons and fermions. And I'll take them, those bosons, to be compact. so that they have discrete spectrum. Okay, so just binding and momentum. So what are these parameters k and k prime? Sorry, this is k prime. So if x7 is S3 cross T4 or S3 cross K3, K squared is the radius of AdS in string units. Sorry, K is radius of AdS squared over in string units squared, and K prime in this case is equal to K because the size of the AdS3 and the size of the S3 are the same. The size of the circle, that size of the T4 is independent, and if you think of K3 as an orbifold of T4, that size is also independent, and the T4 is basically size of T4 is related to the string coupling. It's basically given by the value of the dilaton in this case. If I take x7 to be S3 times S3 times S1, now I will use these three spheres don't have to be of the same radii, they can be of different radii, and I'll use parameters k plus and k minus for them, and k plus and k minus are related to the radius of this of these spheres in string units. Okay, and here k is a harmonic sum of k plus and k minus. Okay, in particular, if you take one of the k's, k plus or k minus to infinity, then you decompactify the 3 sphere, it becomes an R3, and it reduces up to some IR modes to the S3 times T4 example. Okay, but you see the difference between the two examples is the following. In these examples, the global symmetry algebra is, when I write algebras, I will only write one half of the algebra for the CFT. So let's say for left movers, I won't talk about the right movers, they'll have the same algebra. Is SL2R for the AdS3 and SU2 from the S3. And if you have T4, then you have a U1 to the 4. If you have K3, you have no additional isometries. K3 generally has no isometries at generic points in its modular space. For this example, the global isometries is again SL2R for the AdS3 part, but there are two SU2s and a U1. Okay, so that's the difference, that the R symmetry algebra of this example is different. It's two copies of SU2s with different levels, whereas these guys have only one copy of SU2. Now, these solutions preserve, as I said, some supersymmetry. So this global isometry embeds into a global superisometry algebra. So they are, in addition to killing vectors of these geometries, they are killing spinors. And if you combine with the killing spinors, in these two cases, the global superisometry algebra is the superalgebra PSU11/2, which has bosonic subalgebra given by this SL2R times SU2. Notice that there's something funny, but this is expected. So K3, when you take, you can think of these compactifications on AdS3 times S3 times K3 or times T4 in two steps. First, you compactify on T4 or K3 down to 6 dimensions. then you further compactify on the additional S3 down to 3 dimensions. When you compactify to 6 dimensions, T4 preserves more supersymmetry than K3. Okay. But when you further compactify to on S3 with the fluxes, the amount of supersymmetry preserved by both these solutions is the same. There's no enhancement from the T4. It's because of fluxes in the S3. In this example, the global superisometry has to have these two SU2 subfactors, and this algebra has a name. It's called D21 alpha, where alpha is this ratio K minus over K plus. Okay, so it's a one parameter family of algebras which basically tell you what's the relative strength of the two SU2s, relative weight of the two SU2s. Now, these are asymptotically AdS3 geometries. So whatever superisometry algebra you have, that superisometry algebra is just the algebra of killing vectors in the bulk of the spacetime. Since you're asymptotically AdS3, you should allow also large diffeomorphisms, which will enhance, for example, already the SL2 factor via the Brown-Hainaut construction to a full Virasoro. So this superisometry algebra should extend into a superconformal algebra. And this should be the superconformal algebra that the dual field theory sees. Okay, that's the symmetry algebra of the dual field theory. And in this case, this any PSU1, 1/2 extends into what's called the n equals 4, 4 algebra. But for historical reasons, it's called the small n equals 4, 4 algebra. Most people don't make this distinction because most people sort of predominantly talk about that example. But this, the same thing should happen here. And if it, without going into the details, if you count the amount of killing spinors and count the amount of supersymmetries and what the gravitinos are doing in this background, it's the same amount of killing spinors. It's not preserving any more supersymmetry, but it has a very different subalgebra structure because there's different R-symmetry groups with the two SU2s. And so here the superconformal algebra is still n equals 4, 4, but it's a so-called large n equals 4, 4 algebra, which in literature sometimes is called the algebra A gamma, where gamma is related to this alpha by some simple redefinition.
No, you're talking about the algebra of the theory at the boundary.
Correct. Which is not, yes. So this is world sheet. Yeah. The world sheet always has n equals 1, 1. And maybe I will put world sheet subscript to make it clear that it's different. Yeah. And then there are two different algebras from the space-time point of view, and they're different by the virtue of already at the level of the isometries, they preserve different symmetries.
Your goal is to do the world sheet, to show the world sheet theory?
Yes. The goal is to solve the world sheet theory to show two things. First, that the spectrum from the world sheet theory organizes itself into representations of this algebra. Okay, that would, so to speak, derive from a path integral perspective the fact that this is the right algebra for the dual field theory. And second, then perform this step I mentioned here of taking some S transform and extract the physics of BTZ black holes.
I understand what you're doing is kind of deriving Brown-Hainaut strings in a
Correct. I mean,
well, maybe, yeah.
Yes.
A bit more, but that's
actually, let me say it to be historically correct. If you want to derive Brown-Hainaut here, this was done by Hainaut, Liat, Maus, and friends, whose names I'm forgetting, more than 20 years ago. But that follows more or less by applying the Brown-Hainaut construction just to this isometry algebra. Okay, so you'll immediately just start with these algebras and allow generalize the killing vectors to large diffeos, and you will find that these algebras pop out of the game.
you want to read from
I want to do it from string theory. At that level also, I should say that if you were not trying to do the path integral construction, I'm going to sketch out for you. But if you are going to try to do this by just studying the world sheet theory from canonical quantization a la Polchinski, from just writing down Virasoro constraints and doing this, there is evidence that that also works, modulo some caveats, also from about 25 years ago in a paper of Givian, Kotosov, and Seiberg. So they actually constructed vertex operators for the boundary currents. They didn't, strictly speaking, do it for the superstring. They did it mostly for the bosonic string. But the details are similar enough that you can imagine that the sort of structure works out more or less the same. Okay, so that's the setup. And before I go on, I can sort of answer questions. Yes.
So if I remember well, the small algebra can be seen as a contraction of the large algebra.
Correct. So indeed, so
Some limit on alpha.
it's a limit on alpha. Indeed. So as I said before, if you take say k plus or k minus to infinity, keeping the other one finite, then you decompactify one of the S3s. So that becomes an R3. So you get translations. So you can mod out by translations to make it a T3. So indeed you would get the small algebra by that logic. And yes, there are some small subtleties at the level of the algebras, but strictly speaking, most properties at the algebraic level, you can get much of what you want by taking the limit. Okay.
Is it necessary that you specify the text 7 of doing this? Which I would say that the Brown-Hanoff would follow just on
The Virasoro part of Brown-Hanoff will follow. But if you want to actually see what R-symmetry algebras have, you actually need what X7 is. Yes. Yes. Indeed, you're completely right that if I just want to understand the Virasoro algebra emerging, I don't need to do anything. And this is exactly what Givian, Kotosov, Seiberg did. But the details care about what algebra you get cares about what the compactification is. Okay. So in the next 10 minutes or so, I'm just going to quickly sketch how you would do the string partition function calculation. I'll try not to write formulas. Everything can be written in terms of theta functions, but let me spare you the details. But here is the draft logic. Okay. Yeah. Sorry. Yeah. So I didn't say that. So G string is proportional to n1, and this is important for reasons n1 inverse for reasons you will see in a second. It's very important. So thanks. Right. So how would you go about this analysis of trying to write down the string partition function? So the good thing is that all of these are WZW models. Okay, and WZW model partition functions have been known for a long time. If you are doing free bosons, or for example, you can just take the standard answer for the free boson. It's some eta function with some tracing in the numerator for binding momentum modes. With SU2, it's so SU2 is like 3 free bosons, but 2 of those bosons are charged under the other 2. So the answer is not an eta function, it's a theta function, but small detail. And then you have to sort of do some spectral flow to account for null states in the algebra. So the string partition function can be put together by putting all these pieces, and I'll say something about the SL2 part in a second. I can write this as follows. And after I write it, I'll explain what I'm doing here. And again, just to be very clear, I'm suppressing dependence on all the anti-holomorphic coordinates. I'm only writing holomorphic coordinates, and I should explain what my distinction between t and tau is. Okay, so I'm putting one SU2 factor just for clarity. If there was 2 SU2s, I would put another SU2 under U1. If there was a T4, I would just put the T4 piece. So the world sheet is a torus. and I'll take its modular parameter to be T, and I will write Z, the complex structure of this torus is T, and the elliptic norm is e to the 2 pi I T. This world sheet is being mapped into AdS3 times S3 times whatever. And in this space-time, I have a circle whose period is beta. Okay? Furthermore, I have many other circles in the game. I have a contractible circle, let me call it labeled by phi, which is a circle in, so think of this as the angular direction in global AdS3. This is the Euclidean time direction, which has been periodically identified. So I have a torus. So this phi circle is contractible in the bulk. But as I go around this circle, I can twist phi by introducing a chemical potential that gives me chemical potential for rotations along the phi direction. I also have, if I have a 3-sphere, then I can twist the Hopf angles of the 3-sphere to give myself chemical potentials for SU2. So those I'm going to call rho, and if I have 2 of the SU2s, I'll have rho plus for one of them and rho minus for the other one. For simplicity, I will label tau to be I beta plus beta mu over 2 pi to be the modular parameter of the torus on the boundary of AdS3. Okay, so this is, let's say, the CFT modular parameter, which is distinct from the modular parameter of the world sheet. The world sheet modular parameter is integrated over, and it's integrated over the fundamental domain. Okay. Now, I have 2 non-contractible cycles of this world sheet torus. I have only one circle in the target spacetime that's non-contractible. The phi circle is contractible, and the Hopf angles of the S3 are contractible. Somewhere, either on the one pole or the other. If I write the S3 as an interval fibered over 2 circles, so this is one circle, and then this is the other circle. This goes from 0 to pi halves. Call this psi 1, call this psi 2. Okay. I'm twisting along these circles, but I'm allowed to twist because they're not contractible. As long as I go around this cycle, I come back shifted in this cycle by some amount. Good. So these cycles, when they map to the target space, each of these non-contractible cycles on the world sheet can wind around the thermal circle. Those are parameterized by integers, those winding labels, and I'm going to label those integers as M and N. Okay. So one of them you can think of as the world sheet time direction, winding around the space-time time direction. The other is the world sheet space direction, winding around the space-time time direction. Okay. So there are 2 integers, and you can sort of write down the partition function for these 2 integers. So for example, if you just go back to standard analysis of world sheet strings or just 2D CFTs and think of free boson, the free boson partition function is for a compact boson is labeled by winding and momentum, but I can do a Poisson resummation and think of it as a map between a torus to a circle, parameterized by 2 integers. Good. So that's the data. And as I said, the way you work this out is you first work out what the classical action for these simple maps is, parameters by M and N, and the rest is basically taking into account the determinants. And that you can just do from the WCW model analysis. If people want to know what the formulas are, ask me afterwards. I'll sort of spare you the details. There's one subtlety about the SL2 part, so I'll roughly write it out. the SL2 WCW model partition function roughly looks like there's some factors which make it modular invariant, but otherwise it looks like a theta 1 of okay, this is for the holomorphic side. This anti-holomorphic side is the complex conjugate. Okay. Although I have a double sum over two sets of integers which label the windings, I also have the integration domain is a fundamental domain of the torus. It's this upper region in the upper half plane which I have to integrate over. But the first check you need to do before you do anything is to make sure that the answer you write down is modular invariant. The partition functions are modular invariant. They usually are not piece by piece, but after summing over these winding labels. But you can play a game. This game goes either by the name of the Rankin-Selberg trick if you're a mathematician, or Polchinski's unfolding trick if you're a physicist. And the idea is very simple. We have a string, and the string is mapping to a circle in target space. Okay, so that and the windings are basically the windings are two circles on the string into target space. Since the whole sum is modular invariant, I can use the modular transformation to use the sum to fill out this whole domain and remove one of the sums. Okay, so the claim is the integral over the fundamental domain sum over m comma n is the same as the integral over, so if I call this T1 and this T2, it's some appropriate measure, which in this case is T2 squared. But with one sum left over, where the sum now runs from 1 to infinity, not over all integers. This sum is easy to interpret because this says, so this is the string partition function, okay, and this string partition function is a function of tau and rho because I've integrated over the worldsheet moduli. So this gadget better assemble itself in some form of a CFT answer. That's the first thing we need to check. So what is the CFT answer we expect? The CFT answer is the exponential of the worldsheet partition function but if there was only one geometry and fluctuations around one geometry that contributed to the CFT answer, we would get a modular invariant answer for the CFT to get from the beginning. But we are computing the partition function around one saddle point along just thermal AdS. We are not computing the partition function around every saddle point of the string worldsheet theory. So what we should expect is this is a sum over saddles, and that's the thing that gives us a modular invariant answer. What I'm going to do is I'm going to look at only one saddle. So I'm not going to expect anything modular invariant, but I should see relics of these symmetries within that answer already, because otherwise I'm not guaranteed that things will work to begin with. Okay, so that's the logic. I'm happy to take questions here before I sort of spell out some more details of what goes into this. Yeah.
This solar saddle will be SL2 copies of the is what you would be thinking, especially after the thermal AD.
In principle, yes, some of them will be SL2 copies. It's not clear to me whether just SL2 copies will do, just as they don't seem to do in supergravity. It may be that we need something else. In this case, we know what the dual CFTs ought to be. So maybe there's some way to get around it, but that's not the question I know how to answer at the moment. Okay. All right. I glossed over one subtlety in doing this calculation. So let me spell out that subtlety now. The subtlety was when I said the rest, here, this includes whatever part which was not in SL2 or SU2, maybe another SU2, maybe a U1, maybe four U1s, but also the fermions. Okay, and famously, since I'm doing a worldsheet calculation with supersymmetry, I should impose the fermion characters with appropriate GSO projection. So that part is easy. What I have to tell you, however, is when I do the GSO projection, what are my fermions doing around that circle in target space? Okay, so I have a circle in target space, and this circle is not contractible. So fermions can have any boundary condition I can choose, depending both boundary conditions of periodic and anti-periodic fermions are allowed on the target space. So I'll just say in words that the target space boundary conditions if I make the fermions periodic, then I will compute the string worldsheet partition function by computing the trace in the NS sector of the following projectors. That implements GSO projection on one half of the string, and I will put that together with the same GSO projection on the other half. I'm talking about type 2b, so it's the same parallel GSO projection. If I have target space anti-periodic boundary conditions, then this has additional phases which go by the name of the Attic-Witten phases to account for the thermal period of these circles. But see, so this is the calculation one can do, and this is we can do both of these. We can make the choice a priori. But we have one advantage in this game, that we are having the chemical potential of SU2. Right. So that's like the SU2 is an R symmetry from the worldsheet point of view. So ZCFT that I'm computing is either in both, depending on which of these boundary conditions I use, is different. In the first case, it involves putting an explicit -1 to the space-time fermion number, which is different from -1 to the F, which is worldsheet fermion number, of the CFT L0 plus the R symmetry charges for the rho. In the second case, ZCFT is still the trace in the NS sector, but without the -1 to the F. Okay. But you don't have to do the computation twice, because by suitably tuning rho, you can induce a -1 to the F spacetime. Because spacetime fermions have half integer spin under SU2. So if you tune rho to be half plus some rho prime, you'll go from here to there. Okay, and this we can check. One of the few things we checked was that these Attic-Witten phases come out naturally by using this logic. Attic and Witten couldn't do it because Attic and Witten were trying to do this in flat space, and in flat space, this calculation is a bit more tricky. Whereas here, we have sort of explicit SU2 algebras, and we can actually turn on spins. Good. So let's focus on this and realize that what we're computing is a trace in the NS sector. So we'll have space-time fermions, but they'll be in the they will still be in the NS sector. Great. The next statement I'll make is that there's a sort of complicated way. So we've sort of simplified this discussion into breaking up the sum into one sum and doing the integral. Let me write the summand with an explicit M label. And explain what this summand means. Realize that what you're doing is you're exponentiating around every saddle the worldsheet partition function. What I'm computing in this Z worldsheet is the partition function of the single string. When I compute in target space, what I should compute is not the single string partition function, but rather the free energy, and then sum that free energy over the multi-string Fock space to get the CFT answer. So this M sum actually does the sum over the multi-string Fock space of the free multi-string Fock space, whereas each of these pieces is computing the answer for the M windings of the string around the thermal circle. Okay, a singly bounded string is in a single string Fock space, and M times bound string is in the M string Fock space. Okay, so we could just extract the answers by looking at F1 and then realizing that we can do free Bose multi-particling of the answer for the Bose objects that have Bose statistics in the bulk, and free Fermi multi-particling for objects that have Fermi statistics in the bulk. Okay. And if you go through the exercise, you find something simple. So Z worldsheet, so F1 of tau comma rho has two pieces. Which I'll give some superscripts discrete and continuous. So these discrete states are like particles in AdS3, which have definite quantum numbers. They sort of slosh around back and forth. They're like massive particles in AdS3. But famously, in these examples, there is no penalty for strings that sort of wind around the spatial circle of the phi circle that I drew there to sort of stay put at large distance from the in the AdS and move towards the boundary. So you don't get a discrete CFT weights. You get, in addition to discrete CFT weights, you get continuous CFT weights. And that's contained in here. Okay. What I'm going to be interested in is two things, is that these guys have space-time weights of order k, where k, I remind you, is the AdS scale in string units. So they're heavy when the AdS scale is large in string units. They're very, very heavy. So for those of you who are familiar with n equals 4, these are like the Konishi operator and other operators which have gotten very heavy in the semi-classical limit. This guy has two kinds of contributions. It has states of, well, let me say it has three sets of contributions. There are order 1 states, it has order root k states, plus order k states. These are sort of small excitations around the continuum, so we can ignore those. These are coming from string oscillators. But these are interesting because these are the stuff that you see in semi-classical gravity. These are the only things you can see in supergravity because supergravity doesn't know about states which have energies of order of the string mass. So as a first goal, we should check that the states we get are the states which have been computed in supergravity by doing actual harmonic decomposition on X7. Okay. If you get that, then we know that our quantization is correct and our calculation is correct. And then we can proceed to do various things. Okay.
Including also oscillations in the internal space?
Yes. So all the oscillators, when I say string oscillators, are here. All of them are here. In fact, anything that has any string oscillator, it has an alpha prime energy, and it has, that's this root K. Okay. So, and anything that has much higher energy, so these things you should think of as the analog of just excited strings. And these, in some sense, are like excited D branes. They're like giant gravitons in this example. They're the analog of giant gravitons in this example.
Sorry, the central charge of the CFT is about the K?
Is of order K. I'm coming to it in a second. Okay. I haven't told you what the central charge is. It's order N1 times K, but yes. Okay. So, long story short, this works. Okay. So, we get this. But more importantly, we get something very nice. We get the following. We get that this order 1 contribution firstly can be organized very nicely into irreps of the global superisometry algebra. Okay. Remember, we are doing supergravity. Supergravity doesn't know about Brown-Hainow. It's only supergravity plus additional boundary conditions that knows about Brown-Hainow. Supergravity only knows about killing vectors and killing spinors. So this order 1 contribution you can express in either PSU 11/2 or D201 alpha characters. Importantly, at the very lowest level, these characters have two sets of states which contain chiral currents. And the spins of these currents are bounded by 2. In other words, this CFT partition function knows about the Brown-Hainow gravitons through these chiral currents. Okay, so I can write down the formulas, but in interest of time, I won't write down the explicit formulas which I can refer you to in the paper. Yes.
What's surprising is that you get also the Brown-Hainow at the boundary.
Correct.
Without inputting it.
Yes. In particular, since you brought this up. No, they don't come from the long strings. No, they don't. They have nothing to do with the long strings. They never could have come from the long strings. Okay. But let me say something since you brought this up. When people do the supergravity spectrum, the way they do this is they gauge fix gravitons in AdS3. And then they do harmonic decomposition on the internal space. So if you read any of these papers, which are very nice papers, they never see the boundary gravitons because they have gauge fixed and there are no graviton degrees of freedom once you have gauge fixed in AdS3. There are no propagating gravitons, no boundary gravitons. But the string theory is smarter. It has to know about the chiral currents. And since it knows about the chiral currents, when you exponentiate these chiral currents, it will actually reproduce the vacuum character of the appropriate superalgebras. Okay, so this is something we check explicitly that you get the right vacuum character. But importantly, all of these are order 1. the distinction between these chiral currents and antichiral currents is that in terms of characters, these are purely holomorphic functions. These are purely anti-holomorphic functions. Whereas a generic character is neither holomorphic nor anti-holomorphic. So if I pick a CFT state with weights h and h bar, that has its character is not a holomorphic or anti-holomorphic. It's only for chiral currents that the character is purely holomorphic. Good. So now that we have this, I can make my final statement before I go to BTZ. Namely, these currents are distinguished by their chirality, the fact that they have states with one half of the weights being zero, the right movers or left movers, depending on which one I'm talking about. But I can ask you, what is the twist gap of the CFT? Okay, and again, to be clear, this, whenever I'm saying CFT now, I'm just talking about the space-time CFT. I'm not talking about the worldsheet anymore. Worldsheet has been processed and reproduced in terms of some data that looks like space-time answers. Definitely, definitely, most certainly, yes. Okay.
Does it contain stringy states above the boundary order?
No, no, and that's important. The point is that, so you're asking something very important. So this is related to this statement.
Yes.
Okay. For k strictly bigger than 1, okay, which means not necessarily in a supergravity regime, but k is very, very large. But as long as k is just above, the AdS size is just above the string scale, I can make the following statements. Only chiral states are boundary gravitons. There are no chiral currents with spin greater than 2, which means the twist gap is non-zero in this limit. For k equals 1, the twist gap collapses and there are higher spin states. And I say can be present because there's a subtlety here. There's more than one, and that's related to my second other reference from down there. There have been people who've been studying this k equals 1 theory for many years, mainly Matthias Gabardiel, Rajesh Gopakumar, Lorenz Sieberhardt, and others, as a limit of a tensionless string in AdS3. Okay, and in some of the examples, they had to use new formalisms because the limit k equals to 1 is not accessible within the RNS formalism. In in the example of S3 times S1 it is, but let me not get there in interest of time. But it was never clear to me, and in fact our analysis makes it very clear, that there isn't a unique k equals 1 theory if you just take the family of WCW models and go down. Okay, so if you just follow the calculation done here and take k to 1 from the beginning, you'll get some theory. That theory does not have higher spin currents. It's not the tensionless string. So to fix this, Matthias and Lorenz had a paper a few weeks ago where they bootstrapped from first principles a new theory which has a very particular spectrum of just no discrete states, only continuous states. And that theory is not defined by a WCW model, is defined by bootstrap constraints. They actually wrote down 2 and 3 point functions and ensured that they solve the bootstrap constraints. And that theory has higher spin currents. Okay, so whether this theory has a spin twist gap or not now depends on what you mean by k equals 1. If this is confusing, let me give you a simple analogy to deconfuse you. When I say C equals 1 2D CFT, your instinct is, and I say it's non-compact, your instinct is to think free boson. It's a non-compact CFT, it's modular invariant, it just has some IR problems, it's fine. But there's another C equals 1 CFT, which you can get by taking the Virasoro minimal models of various central charges and take that sequence and take C equals 1 along that sequence. This does not give you the free boson. Famously gives a different non-irrational theory called the Runkel-Watts theory, which has different structure constants, different spectrum. Both are non-compact, but they don't have the same structure constants. It's a bit like that in this case, that you get a different theory. Okay. Now that we have the answer and we have a twist cap, I can now make my assertion about BTZ black holes. Since there's a twist cap, when there is a twist cap, the near-extremal BTZ partition function is given by the modular transform of the vacuum character. In other words, I just need to convince you that this piece exists involving chiral currents, and then the BTZ answer you can just read off from there. So this observation is not new. This observation goes back to the original paper of Ghosh, Maxfield, and Turiachi, which was then, of course, cleaned up and made very nice in general context by Iliescu and Turiachi for understanding black holes. So let me say a couple of things in the last, can I take 5 minutes? 5 minutes? This aspect is independent of supersymmetry. I have something to say about supersymmetry. I have one startling statement to make about supersymmetry. So wait for it. Okay. So as Roberto points out, lots of these are independent of supersymmetry, but we can, as I said, we can compute two different partition functions, either with a spacetime -1 to the f or spacetime without a spacetime -1 to the f. So if I compute trace ns without -1 to the f, for this is all CFT, and if I do an S transform, I'll get trace Ramon without a -1 to the f. And BTC black holes live in the Ramon sector. If I do trace ns -1 to the f, then I will get, sorry, if I don't put a -1 to the f in the ns sector, I'll just get trace ns. If I put a -1 to the f, I'll get trace Ramon. So one of them takes me to the Ramon sector, the other doesn't take me to the Ramon sector. So it was necessary that I could do the periodic fermion answer to be able to go to the BTC section. But I can compute everything. So you asked me earlier whether I can do 0,4. I don't have to, because I could just do non-supersymmetric black holes, or I could do supersymmetric black holes. Okay, so let me just say the word about non-SUSY. In this case, the prediction would be that you get t to the 3 halves, and this is coming from AdS3 part or Schwarzian or what have you, times some other powers of t, which will come from the R symmetries. But if you work in the sector with fixed charges, which you can do very easily in this case by just summing over the modular images, this factor goes away. So the universal prediction that you get t to the 3 halves is just true in the canonical ensemble with fixed charges. What's more fun, and this was the original calculation of Iliescu, Hedman, Toriaci, and Zhao. Since I can compute the trace in the Ramond sector, and I have chemical potentials to tune, we can compute can be converted into trace Ramond minus 1 to the F space time by tuning the Ramond the R symmetry chemical potentials appropriately. And so from here you can get the elliptic genus. And if you do the small n equals 4, 4 superalgebra, you see that states with 0 R charge are BPS, and they live on the BPS locus. And there's a exponentially large number of them. That's what's called the index. And then there's a gap, and this gap starts out with a continuum, and how much the gap is depends on what the R charge is. Okay. Good. Now you might think that this is a generic statement, and since I have almost out of time, I'll end with a provocative statement that you can do the same calculation in the large n equals 4 algebra. And in that case, there is no BPS degeneracy. The gap extends all the way to the BPS case. And in fact, the index, should you compute it, which we did, and so did this other paper of Matt Hawking and Hawking student Zhao Yi, is temperature dependent. It's not holomorphic. Okay, so this is something that was known but not very well appreciated. But the picture is drastically different for large n equals 4. The BPS states are not gapped. Okay.
In terms of the original black hole, what is the difference between the small and the large?
The difference is the global symmetries, the different R symmetries. So if someone tells you, so it's good you brought this up, if someone tells you they're doing something for BTC black holes, you should ask them what theory, what R symmetries, because the answers care about what symmetries and what R.
If you come from the higher dimensions, then you land on the small equals.
If you do, depends what compactification you do. If you do T4 or K3, yes. If you do S3 times S1, you land here.
Is this a statement that applies for the stringy?
No, it's a statement that applies away from the string theory.
Then
it
may even begin with n equals. I mean, I need not have a.
Correct.
N equals to 4 dimensions. N equals to supergravity in 4 dimensions. I have a Nostrom.
But you won't land here. You won't get large n equals 4.
I want to get that.
Yes. You land on the other one. Yes. Yes. Yes.
In order to get here,
you need a different compactification. So the only examples that we know of, and this is sort of a bit more extensively discussed also in this paper of Matt and friends, are AdS3 times S3 times S3 times S1. Or there's an M theory construction by Skenderis and friends, which gives you this. But typical black holes do not see enhancement to large n equals 4. They don't see two SU2R symmetries.
So is S3 cross S3 cross S1 you land there. S3 cross T4
you don't land there. Yes.
So
everything we know is consistent, but yes. But this example is very funny.
Yes.
I can say a lot more about this and BPS representations, which are very funny in this case, and that's where all the funny business comes from. Yes, yes, it's provocative. It's not outrageous, and most of it is kinematic, so it's much less startling once you understand the kinematics. Okay, sorry for going a bit over time. Let me stop here.
Are there more questions?
A comment more on this K equals 1 theory. Does it correspond to some K equals 1 CFT, or is it several different CFTs with different central charges?
Oh, so when K equals 1, the central charge is 9. So this has to do with the fact that it's really three-dimensional. So the central charge, which I never wrote down, is a function of K. From the worldsheet point of view, is 3K over K plus 2. Sorry. No, something happened. No, the 3K over K plus 2 is SU2 answer. Sorry, this is this. Yeah. You have to shift the levels. When I say K equals 1, I mean N equals 1 supersymmetry K equals 1. Shift the level by 2.
Was there some parallel CFT and you have some different CFT similar to Liouville?
Yeah, so in some sense this is like Liouville, but not quite the same thing. So since you brought this up, like I could say it the following way. The C equals 1 example I gave you. The free boson is one theory, but there's also you take the Liouville, which exists for C greater than 25, and you can analytically continue it for C less than 1, or you can analytically continue complex domains and come down to C equals 1. The analytic continuation above through the complex domain down to C equals 1 is supposed to be the limit of these minimal models, and that's the Runkel-Watts theory. But the structure constants are given by Liouville structure constants, they're not given by the free boson structure constants. Free boson structure constants are of course boring. They just pure momentum states, and then they have order 1 structure constant. So this theory is a bit like that. The one that Matthias and friends and Lorenz are proposing is a bit like a Liouville theory, but I would use the words time-like Liouville theory, if that makes sense, to explain what that theory is. I think it will be good to understand it. What they have done is basically they wrote down, they postulated a spectrum, they postulated structure constants for the spectrum and checked crossing for 4-point functions and convinced themselves numerically that it works, which is good enough evidence that this is a bona fide CFT. In bosonic language, maybe what I should have said, it's K equals 3, because in the bosonic language, K equals 3 is the right limit.
More questions? So if not, we thank again Mukund.